Now we'll delve into the next part, which is heart rate and heart rate variability and movement. And before I do that, I want to remind you of a little bit of what I discussed last time in the part one of the autonomic nervous system and sleep talk. And I sort of emphasized there that to me, this is sort of my personal theory, is that non-REM, particularly slow wave sleep, is a time to establish and define self. And this is taking it from an information theory perspective. And I think that sleep is a way to establish, what is constitutes me and what is not me. And then non-REM sleep particularly emphasizes the internal consistency. And this is why slow wave sleep, non-REM sort of stage three, is the time for cleaning and detoxing. This is when the lymphatics is most active. This is where you have immune memory consolidation. This is a time when you have pruning of unnecessary neuronal connections. So it sort of makes sense to me that from informational theory, this is the time where you're like in deep sleep, you're ignoring everything outside, you're focusing inside and figuring out what is self and what's not self. And this is manifested physiologically by two ways. First is the autonomic nervous system. As you go deeper into non-REM sleep, you have a predominance of parasympathetic nervous system and then a cool down or a decrease of the sympathetic nervous system. And you see this sort of gradually from non-REM 1, 2, and 3. The other sort of physiological changes that we see is coherence and synchrony. So basically, as you go from non-REM into deeper stages of non-REM sleep, you have increasing stability of order. In non-REM one, for instance, what I mean by that is that there is not much of a regularity to the signal. But as you go into non-REM sleep, it becomes more regular. And the other important thing is that there's a lot of coherence that happens at this stage. And what I mean is that, for instance, the heart and the lungs seem to increasingly be synchronized and coherent, particularly in the high frequency range. And then you see other parts, like even delta waves that you see in the brain in the EEG that seems to correlate with some of the parasympathetic changes that you see in the heart and breathing, for instance. So this is just sort of the two things that I want you to keep an eye out on as I continue to go into the autonomic physiological changes that you see in non-REM stages. So REM to me is a time to redefine the new self. And what I mean by that is, you or go out in the world, explore, you incorporate new things, you take some new lessons, you expose yourself to the outside world. Non-REM is when you sort of restore the self, eliminate some of the excess noise. And then REM is the part where you incorporate the key lessons and exposures from the earlier in the day and to integrate into the new self. And what it is, it sort of frames these new lessons and exposures into a larger context. And it does this by letting these like new lessons and exposures gain widespread exposure to the whole. It's kind of like a hazing event for a fraternity or even an initiation ritual for a gang. It's like chaotic, it's unpredictable, yet widespread. And it's taking these new lessons and allowing the whole body and brain to interact with it and to recognize it and incorporate it within a larger framework. And so this process entails both an activity of both sympathetic nervous system and the parasympathetic nervous system with a little bit of a bias towards sympathetic nervous system. And the other thing is this process is quite unstable and disordered. So again, I want you to focus that when we take a look at the heart rate variability and respirations and other things, we are going to see a predominance of sympathetic nervous system, also highly variability and some disorderliness as well. And just to show sort of demonstration of these features is we could see the studies that have been done on MSNA, like muscular sympathetic nerve activity. And this is an image of the needle that's penetrating into the coronial nerves. And it's assessing the activity of the firing of the sympathetic nerves going to the blood vessels. As we see here, this is awake time, and you can see the sympathetic nerve activity having decent amount of activity. This is the blood pressure that sort of correlates with this. And then as you go from non-REM, the light stages of sleep to deeper stages of sleep, you see that the activity in the sympathetic nervous system significantly decreases. You also see less variability in the blood pressure as well, so that it becomes quite stable. During REM sleep, we see that there is activation of the sympathetic nervous system, and it's quite active, and there's a decent amount of variability as well. And then you can see that in manifesting in the fluctuations of the blood pressure as well. So when you take a look at heart rate, like again, heart rate is a pure reflection of the balance between the sympathetic nervous system and the parasympathetic nervous system. And so this is an image of heart rate over the night and the hypnogram with wake non-REM 1 through 4. This should be 1 through 3. I guess this is an older study. And you could see that at least in the non-REM stages, particularly in the deeper stages, the heart rate again is at the lower rate and it is stable. And particularly here, you can see as it goes from sort of REM, I guess it's REM, and then non-REM 2 and 3, you can see the heart rate sort of stabilize and then decrease as well. And that's again sort of emphasizing what I talk about is that during this stage of non-REM, as you go deeper, there's a greater parasympathetic nervous system activity and there's more stability as well. And so for non-REM one, you have your heart rate is about resting heart rate that you find during the day. By N2, it decreases about 15 to 20% approximately. Again, this is like an approximation. It's not true for everyone. And for N3, about 20 to 30% reduction in heart rate. For REM, you could see again, so at these stages of REM, you could see it's demarcated by this hypnogram here. You could see the heart rates that are correlated with REM sleep, and you could see that it's highly variable and it's quite dynamic. And oftentimes it can exceed sort of the wake resting heart rate as well. So that is a quick summary of heart rate as we take a look across the sleep stages. Now, how about heart rate variability? These are representative samples, 90-second windows of heart rate from each stages that we see here. This is wake, N1, N2, N3, and REM sleep. And then we also see the heart rate variability, the power distribution, and this was using wavelet analysis. And what we see here, again, this green dashed line represents the frequency at which the respiration is occurring. So when there's a peak here, this denotes the respiratory sinus arrhythmia, but fluctuations in heart rate that occurs with respiration. And you could see that in terms of the heart rate, as you are going into deeper stages of non-REM, again, the heart rate decreases, and then a little bit less fluctuations in the rhythms. When it comes to heart rate variability, you see that the total heart rate variability actually decreases. So what I mean by the total power is the total area under the curve across the whole distribution across the x-axis is higher in wake, and then it decreases as you go into deeper stages of sleep. However, when you focus on the high frequency heart rate variability, which is at the frequency that, again, associates with breathing, we see that the proportion that is associated with breathing is greater than the other parts, particularly the low frequencies. So you see a decrease in the total HRV power, an increase in the proportion of high frequency heart rate variability. For REM sleep, in this case, I guess the heart rate's on the lower side, but you should see a little more fluctuations. And because of this increase in fluctuations like that I had mentioned before, the total heart rate variability power, or the area under the curve, is greater. And then the high frequency power is sort of variable. It can sort of go up and down, but importantly, it tends to sort of favor the more of the low frequency and the very low frequency during the REM sleep. So again, as a review, total heart rate variability of power and SDNN, particularly if you're doing it, so the standard deviation across the 1 minute, these things go down as you go deeper into non-REM sleep. And then REM, there's an increase because of the involvement of both the sympathetic nervous system and the parasympathetic nervous system. When we're talking about high frequency HRV, this is the frequency domain, and also the time domain as RMSSD, which is the root mean square of the successive differences. This is representation of the parasympathetic nervous system. This tends to increase as you go into deeper stages of non-REM sleep. And the important thing is the end part. This is the normalized part of the high frequency. So because the total HRV decreases, if you just focused on the high frequency power itself, in other words, the area in the curve just around the breathing, that also can decrease. However, it's the normalized, it's the proportion of the power that is focused in the high frequency that increases. So that's what I want you to sort of evaluate when you're doing this in your uh, evaluation of heart rate variability. And again, in REM sleep, you have a reduction in the normalized high frequency and a reduction in RMSSD. I want you to also notice that the RMSSD doesn't go into three arrows here. In other words, it doesn't increase in stage three sleep. And then I'll explain a little later as to why that is. Okay, so that's heart rate and heart rate variability. Now, how about muscle activity? Now, when you have a polysomnogram, you often have EMGs. EMGs is often placed on the chin or in the anterior tibialis on both legs, which is on the leg. And you also have electroculograms. So you could have this on the temples to assess actions, movement of the eyes. And so you have the sort of the characteristic features on this illustration of the changes that you see in EEG during wake. So, like beta rhythms, for instance, in stage one, you have some theta rhythms. Stage two, you could see some K complex and sleep spindles. Stage three, you see the delta waves. And then REM sleep, you could have sort of theta rhythms again as well. Electrooculagram during stage one, you have basically these slow rolling eye movements which then go away. And then in stage three, it should be practically having minimal movement of the eye. And then during REM sleep, this is the rapid eye movement that you see here as well. Now, when it comes to muscle activity, we should focus largely on the EMG here. And what we are seeing here is the change in tone. And so during wake, you could see a lot of this activity, like this noise that you see here. And that it represents a lot of the small sort of neuronal activations that are happening at each of the motor unit, not at the larger muscle overall, but at these motor units that are not manifested as actual, physically visible movement. And so what happens is that these EMG tone decreases as you go deeper into non-REM sleep. And so you could see these fluctuations decrease. In REM, you should practically see a disappearance of that. And that has to do with the muscle atonia that you get during REM sleep. And it's neurologically, you have the sublateral dorsal nucleus, which goes to the spinal column to inhibit the activities from the brain to the rest of the body. So this is what the polysomnograms are you looking at to differentiate often REM sleep, for instance, from non-REM sleep. And this is sort of the summary of what I showed in that graph. But when it comes to wearables, we don't have EEGs, we don't have EOGs, we often don't have EMGs either. And what we rely on are accelerometers. And accelerometers assesses muscle movement. And this is different than the tone that you see in EMG. So these things that you see on EMGs, you can't necessarily see on the accelerometer. And so I just want you to be aware of that. On N1 sleep, you will occasionally register like these sudden like muscle twitches using the accelerometer. These are called hypnic jerks. And N2, you'll notice reduced muscle movement. In N3, you have basically the least amount of movement, and it's uncommon to see any postural shifts. You're not going to see people sort of moving from one position to the next during non-REM sleep, 3 sleep. During REM sleep, you have temporary paralysis. Again, the muscle atonia that I talked about. The only areas that you do have movements, or at least in normal, healthy individuals, are the eyes, muscles, and then the diaphragm. And occasionally you will see acting out of dreams during phasic REM. And you could see this actually in this breakdown. So you could see here a accelerometer. This is a 3-axis capacitive accelerometer. And then you could see the counts. So this is the actigraphy counts that are derived from the raw accelerometer data. And then this is corresponding to the stages of sleep. And you notice here that REM sleep, although theoretically you should have little movement because of muscle atonia, you can still see that there is decent amount of movement during REM sleep because probably in some individuals you're acting out your dreams. And so this shows the counts, the activity counts increasing here as well. And so in summary, what you anticipate to see in changes in muscle tone is from N1 to N3, a reduction in the muscle tone EMG, and then basically an absence of this tone. But again, this is available on PSGs in the laboratory, not often in wearable devices that are out there. What we have available through wearable devices are the activity counts from the accelerometer. And so that we can assess that with non-REM, you should also see some reduction on the activity counts as you go into deeper non-REM sleep. But for REM, it is not always that straightforward. Ideally, you should have reduced acceleration or any type of activity during REM sleep. But because some people act out their dreams, you can have also activity here as well. So that's the summary based on heart rate variability, and muscle activity based on the 3 stages.